Okay, so what I want to talk about in this lesson is the idea of rates of reaction. So I want to try and go through and explain what that means. So we have this idea of a rate of reaction. And when we talk about rate of reaction, we're talking in relation to a chemical reaction. So rate really can be, it can be related to how fast something happens. So how fast something happens. Now, if we think about chemical reactions, and chemical reactions are just really like changes that can be observed. So we're talking about how fast does the reaction happen. So remember, if we think about, so if we have a look here, so what we have here, so we have a balloon that's filled with hydrogen. So hydrogen, and it's in the air. It's in the air. So we can see here that that there's air, and one of the components in air is oxygen. Okay, there's lots of other stuff as well. There's hydrogen, there's nitrogen, and there's oxygen, nitrogen, and water vapor. So if you take a lit splint, for example, and you put it into contact with hydrogen, what happens is you get this huge explosion here. So you get like an explosion. So what happens is you get this really fast change that happens. So the hydrogen, in the presence of, like for example, heat that's supplied from the flame, you get it connects with the oxygen very, very quickly. It causes this massive reaction and it releases water vapor, H2O, in gas form. Okay, so what we can do is we can actually model this what we see here in a chemical equation like this. So what you have is you have hydrogen coming into contact with oxygen. You have a catalyst. A catalyst is something that can speed up or slow down a chemical reaction. So the catalyst in this case is the flame, which is heat. So that's what kicks off the reaction. So you have the reactants, and then you have a flame that it comes into contact with it. And what happens is you get the hydrogen that's in the air, hydrogen that's in the balloon, should I say, it reacts very violently with the oxygen that's in the air. And you get water produced, water vapor, and you also get a lot of energy, which you can see here. Okay, you can see in the form of light, and there's also heat, and you get water formed. Now, this reaction is very, very fast, very fast. So it happens instantaneously, as in like within the blink of an eye. So within the blink of an eye, you get reactants being changed into products. And that happens very, very fast and very rapidly. Now, on the other hand, if we have a look here, so what we have is rust. And again, this also is change that happens over time. And it's so what happens is you have metals such as iron. Okay, so you have iron in some of these metals. And what happens is it comes into contact with oxygen. So imagine there's iron, let's say you have, let's say, an iron chain in this case. And what happens is you have oxygen molecules in the air and they come into contact with the iron. And what happens is you get this chemical reaction. So again, you have the reactants here on the left hand side, and you have the products on the left hand side. And what if you get moisture or water, that starts this reaction happening. And what happens is basically the iron and the iron, so the iron that makes up the structure here, the oxygen starts to stick onto it or bind with it, and then you get this substance that's known as ferrous oxide, which is also known as rust, and you get this distinctive change that happens. So it goes from a nice shiny chain or a nice pleasant looking chain, and over time it starts to rust. Now this is an extremely slow process. It can take it can take weeks and months for this reaction to happen. But nonetheless, both of these things are chemical reaction. The only thing that's different besides the reactant and the products is the time it takes for this to happen. So the time. And this time in relation to how fast a reaction happens, this is what we mean by rate of reaction. So it's how quickly or how long or how much time it takes for the products or the reactants to be converted into product. And this is what we mean by the rate of reaction. Now we have a very specific definition, and I'll show you this here in relation to it, and we'll start to look at it in a little bit more detail. So the definition, the formal definition, and these definitions are important as well, that you learn them and you kind of know what they mean. But so the rate of a reaction is defined as the change in concentration per unit of time of any one reactant or product. So if we think about that, so when we start off, okay, we have a certain amount of our reactants. So let's say in the case of this reaction here, our reactants are hydrogen and oxygen. So at the start, before these come into contact with each other and react, there is a certain amount of it, okay? So let's say, so there's a fixed amount. So we might have, imagine we have 1, 2, 3, 4, like this is all of our hydrogen, let's say, and we'll have a fixed amount of oxygen as well. So imagine this is our oxygen, like so. Now what's going to happen is over the course of the reaction, these are going to combine together and you're going to get water being produced, like so. So as a result, as the reaction goes on, the number of hydrogen molecules decreases. The number of oxygen molecules decrease. And what's going to happen here in relation to the products being formed, the number of water molecules being produced is going to increase. So as the reaction takes place, the amount or the concentration of the reactants changes. So the concentration of the reactants goes down, whereas what happens to these reactants, they get joined together and you get product being produced. So the amount of product increases over time. So what we can do is we can like, let's say we can use a stopwatch and we can time how long this takes to happen. And this is what's known as the rate of reaction. So the same here with the iron. So again, you have, so as this reaction takes place, the amount of iron decreases, the amount of oxygen decreases, and the amount of rust increases. But it takes a lot longer for this to happen. It's a slow reaction. Whereas this reaction here, it just happens instantaneously. So you get this massive reaction, you get like an explosion, and that is what an explosion is. Explosions are very fast reactions and they produce large volumes of gas in a very, very short period of time. So whereas if you take Ruston, it takes a long time for that to happen. And that's what we mean. So basically, this is the definition. The rate of reaction is defined as the change in concentration per unit of time of any one of the reactants or the products. So the reactants decrease as the reaction happens and the products increase. And it's the time it takes for that to happen. That's what we mean by the rate of a reaction. And we can even start to look at this and put like a formula on this idea as well. So, and this is something that I just want to show you. So if we take something, we have this guy here. So we can look at it mathematically then as well. So from a mathematical point of view, the rate of a reaction then is the change in concentration. So it's the change in concentration of any, for either the reactant or the product, divided by time. So that would be like, let's say, so this is your word definition, and then this is like your mathematical definition that we can use. So rate of reaction is the change in concentration of any one of the reactants or products over time. And in a lot of ways, it's kind of similar to if you take, so for example, speed is equal to distance over time. So a way to think about it is speed is like how distance changes in relation to time. Now instead of the rate of reaction, the rate of reaction is like the speed of a reaction. And what does that mean? It means how quickly product is being changed, or how quickly reactant is being converted into product. That's what we mean. So in this case, it's going to be like how quickly is the hydrogen and oxygen being converted into water, or in this case, like how quickly is the iron and oxygen being converted or changed into, or that change happening and changing into ferrous oxide or into rust. So that's what we mean. That's the definition in relation to the rate of reaction. So if we're to have a look at, like, let's say just a more kind of formal example of this. So this here is an experiment that can be set up, and it's fairly straightforward. And this is a graph showing the course of a reaction here. So what we have here is, so we have our products, our reactants are hydrogen peroxide. So this is what it looks like. So this is known as hydrogen peroxide. And what we can do is we can react this with a catalyst, which is this MnO2. And this is what's known as magnesium dioxide. Sorry, manganese dioxide, should I say. So in the presence of this, okay, so imagine here, so we have this liquid here is the H2O2, and then this substance in here, this black substance, is the MnO. So what happens is these come into contact with each other and it starts a chemical reaction. It starts a change process happening. So what happens is, see the way this is hydrogen connected to oxygen, the hydrogen and the oxygen start to come apart. And what you get produced then are, so you get H2O, which is just water. And you get oxygen produced as well, which is O2 plus oxygen. So these are, so here this is your reactant, and these are your products that are produced. So basically what happens is, in the presence, so hydrogen peroxide, which is this substance here, in the presence of manganese dioxide, this is a catalyst, and you get these products being produced. And you can set up an apparatus like this. So all this is this is just a jar that contains the hydrogen peroxide and the manganese dioxide, and they are put into contact with each other here, and what happens is they start to produce. So you're going to get, for example, O2 oxygen, O2 gas being created in here, and you'll also get water as well. Now what's going to happen is the oxygen is going to travel down this tube, so it's just a glass tube. It's going to go in underneath here, and then it's going to bubble up here like this, and it's going to start to fill this space up here. And as it fills the space up here, as more and more oxygen is produced, the level of the water is going to decrease. And what we can do is we can measure this. So this is a graduated cylinder, and you can measure the amount of oxygen that's being produced. And what you can do then is you can use a stopwatch, and you can time how long it takes, for example, for this level in the water to decrease down to a certain level. And that will tell you, for example, how much oxygen has been produced. So as this reaction happens, the amount of oxygen is going to increase. So the amount of water is going to increase, and the amount of hydrogen peroxide is going to decrease. So because this is going to be broken down, so it's going to decrease. And you're going to get an increase in water and an increase in oxygen. And then what you can do is you can add in this time element. So you can measure, for example, how long it takes for this water level to drop to a certain level, And what's causing that to drop? Well, you get oxygen being produced up here in this space, and it pushes down the water. So it does. And as a result of that, you can time then, you can look at, if we remember, so if we think about the reaction, so the rate of reaction is the changing concentration of any of the reactants or products over time. So what we can do is we can just focus on one of the products being produced. So we're focusing on oxygen in this case. So we're just focusing on the product, one of the products being produced. And what we can do is we can set up a apparatus like this. We can set up this experiment and we can run the experiment, set a timer, and then watch as the water level decreases. And then when the water level decreases, that indicates that the reaction has stopped. And then we can stop our timer. But what we can do is over time, we can take a couple of different time intervals and measure the amount of the oxygen that's being produced. Now what we can do here is we can take this information from this experiment and produce a graph. So we have in the graph here, we have the x-axis and we have the y-axis. And what you're getting is, if we look along the bottom, you have time in minutes. So you start off at the start, you start your timer, and at 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, 6 minutes, 7 minutes, and 8 minutes, you would be checking the level. So you check the level of the water, or the level of the gas here, the oxygen gas that's being produced. So how much is it pushing down? And you can just measure off, or read off the, let's say, the level of the water in relation to the graduated cylinder. And then what you can do is you can measure the concentrate. You can put in like what you've got. So let's say, so at the start of the reaction, let's say the water level is at a certain level. And then after 1 minute, we have a look and we can see that the volume of oxygen is 10 centimeters cubed. Okay, so you can see that we have like about 10 centimeters here. And then as time goes by, so 2 minutes, that's an increased up to about 25. You have a volume now of oxygen of 25. After 3 minutes, you have a volume of 30. After 4 minutes, you have a volume of around 35. 5 minutes, you have a volume of just below 40. 6 minutes, you have a volume of 40. 7 minutes, still a volume of 40, and 8 minutes, still a volume of 40. So you can see here it starts to level off. So what we have here then is we have like a reaction curve. So we can see like how the concentration, remember, the concentration of our, in this case, oxygen, how the concentration of a product, how that's changing in relation to time. And you can see here, so at the start here, you can see that the slope is very, very steep, or the amount of change is steep. So you can see here that this part of the reaction is very fast. So the reaction is fastest near the start of the reaction. So at the start, it's pretty fast. Then what happens is the reaction starts to slow down. So you can see that this curve starts to kind of level out. So the concentration starts to become more even or level. And then what happens is it levels off at about 40 cubic centimeters. So you're not going to get any more oxygen produced. So the rate has stopped and no more gas is coming off. So what happens is it just levels off. And this level stops dropping. The level of the oxygen stops dropping. So what you can see here is that, the steeper the curve here, the faster the reaction is happening. And you can see that it happens. So what we can see is if we look over the whole course of this experiment and the course of the chemical reaction, we can see that, it takes about 6 minutes for this reaction to start and finish. So it takes in around 6 minutes. So 6 minutes is when this curve starts to level off and you're not getting any more oxygen produced. So what we have then is we have an amount of oxygen being produced. So we have 40 cubic centimeters of oxygen produced in about 6 minutes. So what you have is you have a concentration, and you have a concentration of a product, and then you have a time as well. So what we can do is we can start to use this formula then to actually work out and put a number on the rate of the reaction in relation to hydrogen peroxide and magnesium dioxide. So in this case, what we can say is that the time it takes, so the time taken, and so time taken, and let's just move across a little bit just so we have some space to work. So in the case of this reaction, the time taken is equal to, and we can read it off the graph, it's 6 minutes. And the change in concentration so the concentration is equal to 40 cubic centimeters. 40 cubic centimeters. So that's the concentration. And then what we can do is, so we can say that the average rate, or the rate of the reaction, in this case is going to be equal to the change in the concentration of the product, which is 40, divided by the time it took for that concentration to change or be produced, which is equal to 6. And if we divide them into each other, that's equal to 6.67 centimeters cubed per minute. Okay, so this here is the rate of the reaction. So again, this is just a general kind of introduction to the rate of reaction. Now, another important kind of idea to think about as well is this here. Okay, so in the case of this reaction, we have this guy here, which is what's known as a catalyst. Now, there's a particular definition on a catalyst as well that it's important that you kind of know the definition and you know, you know what it means. So a catalyst then, I'll just give you what the official definition is of a catalyst. So this is what a catalyst is. So a catalyst is a substance that alters the rate of a chemical reaction, but is not used up in the reaction itself. So if we think about our catalyst here, let's just bring this up a little bit. So our catalyst in this experiment is magnesium dioxide. So what will happen is when this reaction happens, this reaction doesn't change, or this material doesn't change. It just stays there as such. Okay, so it doesn't get consumed in the reaction. But what it does is it helps the hydrogen peroxide to break up. So it does. So in the case of a catalyst, so then a catalyst is a substance that alters the rate of a chemical reaction. So it will cause the reaction either to speed up or it will cause the reaction to slow down, but it's not actually consumed in the reaction. So the reactant, it stays there and it doesn't change itself. But what it does is it'll either cause a reaction to happen faster or it'll slow down a reaction. And that's like your official definition of a catalyst. But again, we'll look at more examples of this and it'll hopefully become a little bit more clear as well. So if we think about our other reaction here, our catalyst in this case would have been the flame or the heat, the flame, okay? And that flame isn't consumed, let's say, within the reaction either. And the same as well with like water as well, okay? So when you take rust, the water, the catalyst isn't consumed in the reaction. It doesn't become part of the product that's produced. So that's what we mean by the rate of a reaction. So there's a lot there in that lesson, but again, we'll go over this over time. So just have a look over it, think about it, and we'll start to look at like what are some of the factors that will affect how fast a chemical reaction happens. Okay, so thank you for listening.